Lesson 28 in Theory of Road Vehicle Motion. Get ready to dive deeper into the rolling resistance of a tire. In this lesson, we're uncovering all the key factors that affect this resistance. We already covered why this resistance exists and how it manifests itself on the tire in the form of torque that is opposite of the rotation of the tire. Remember the lesson from one of the previous sections. This is the second lesson in the section on resistances to motion. Rolling resistance represents a sum of various different factors, but in one of the previous sections where we talked about the elastic tire running on a rigid surface, we discussed where do these losses of energy come from, and we mentioned this little thing called hysteresis. The hysteresis resistance is the most important and the most dominant factor for rolling resistance. In normal conditions of road vehicle motion, the hysteresis is accountable for 90% of the rolling resistance. So hysteresis is the most dominant factor when talking about the force and ultimately the torque of rolling resistance. Now we're going to go over some of the characteristics for the hysteresis resistance. The first one is that it is generated because of the internal frictions that occur because of the constant deformation during rolling. The tire is rolling and it is constantly deforming. We covered how and why this happens in more detail in the section of rolling an elastic tire on a rigid surface. This resistance, however, also exists while the wheel is not moving, while it is static. So here we have a diagram of a tire that is a wheel or a tire that is rolling, it's in motion, but the rolling resistance, the hysteresis resistance, also exists when the tire is static. So this means that we have to act on the wheel with a certain force to even get it to start to roll. The hysteresis resistance increases with the increase of radial deformation of the pneumatic tire. This means that if the tire is softer, in other words, more prone to deformation, that softer tire will have more hysteresis resistance to it. Of course, the softness or hardness of the pneumatic tires depends on the pressure inside of it. So a pressure increase inside of the tires will decrease the amount of deformation and ultimately decrease the hysteresis resistance. However, pressure inside of the tires is not the only factor. The materials that make up the rubber compound also determine the hardness of the tire. The hysteresis resistance is proportional to the vertical load on the wheel and the coefficient of rolling resistance F. We already talked about it. So it basically means that the vertical load on the tire, aka the percentage of the vehicle's weight that is distributed on the given wheel, times this coefficient is basically the rolling resistance. So the rolling resistance depends on the rolling resistance coefficient and the vertical load that's exerted on the tire. In other words, the vehicle's weight, right? It is interesting to see that the value of the rolling resistance coefficient, which again directly affects the force of rolling resistance, is almost constant or it has a very slow rise. Now remember, these are 0.1 and this is 0.015. So this is very zoomed in when we take a look at this graph. But it's almost constant at a certain speed range. We can see a very small increase from 0 to 80 kilometers per hour. But when we increase speed more, we can see a drastic steep increase on the function. So for higher speeds, it increases significantly. Remember that in normal situations with normal speeds, the coefficient of rolling resistance F is around 0.01 to 0.02. It is 1% to 2% of the vertical load on the tire. Remember the equation. Now, tires roll and deform while the vehicle is in motion. This all creates heat. In other words, the hysteresis resistance, the energy we lost from this phenomenon, is converted to heat energy. This heat influences the pneumatic tire in raising the temperature. By raising the temperature of the pneumatic tire, the hysteresis actually decreases. Why? Well, with the increase in the temperature, the pressure also rises inside the tire. When we have more pressure, we have less deformation of the tire, therefore we have less hysteresis losses. This means that when the vehicle starts to move, it will take a certain amount of time to heat up the pneumatic tires in order to reach this equilibrium where the temperature remains constant, the temperature of the pneumatic tires. This is usually in 30 minutes to 1 hour of driving. After this, there will be less hysteresis losses in the tire. In the beginning of the lesson, we said that hysteresis resistance accounts for about 90% of rolling resistance. What about this 10% or sometimes more that's left? Well, we have the friction in the bearings of the wheel hub that take up some of the energy and convert it to heat. We have the resistances of uneven surfaces. Because it is an uneven surface, it is prone to deform the tires more, and ultimately we have more hysteresis losses. We have the resistance of the side direction. In this picture right here, we can see the force Fy that occurs while steering or when the vehicle is in a curve. This will also give us unwanted resistances. Squeezing out layers of moisture and dirt from the surface also takes up some of the energy, as well as the tire sticking to a wet surface. Now, in our assignment, we will have coefficients of rolling resistance, and we won't get too much into these details. This is it for the lesson on rolling resistance. In the next lesson, we will be talking a little bit more about rolling resistance factors, just because this is very important to us when designing and analyzing the resistances to motion on a vehicle. Remember, the rolling and drag resistances are the most dominant ones. Thank you for listening and for staying focused.